All right, so here we have what's referred to as a ballistic pendulum. The word ballistic just refers to a collision, and it's a pendulum because this bullet gets fired into this hanging block, and then as a result of the collision, the bullet block combo is going to swing like a pendulum. So it's called the ballistic pendulum. So we're given the mass of the bullet as 15 grams, which we want to put into kilograms. 0.015 kilograms. The initial velocity of the bullet is not known. That's actually what we're solving for in the first question. We're given the mass of this hanging block as 2 kilograms, and it's initially at rest. It's just hanging there. So the collision happens. The bullet goes into the block. The two become one. So this is perfectly inelastic. That's the term for when two objects collide and become one. And as a result of the collision, the bullet block combo swing up a vertical height of 0.1 meters and come to rest for a split second. So up here at the highest point, the velocity of the bullet block combo goes to 0 before it swings back down again. All right, so we're solving for the initial velocity of the bullet. So since we have a collision, the bullet collides with this block, we're going to be using conservation of momentum. So m1 v1 initial, the initial momentum of object 1, plus m2 v2 initial, that's the initial momentum of object 2, is going to equal m1 v1 final plus m2 v2 final. But because the two objects stick together in the collision, these velocities are the same. So what we can do is we can factor out, so I'm going to rewrite the whole thing, m1 v1 initial plus m2 v2 initial. We can factor out these velocities. So this becomes m1 plus m2 v final. The initial velocity of the hanging block is 0, so v2 initial is 0. And we're being asked to find the initial velocity of the bullet, which is v1 initial. So v1 initial will be m1 plus m2 times v final over m1. So in order to solve for the velocity of the bullet before the collision, we now need to figure out the velocity final immediately after the collision. So this bullet hits the block. So imagine this happening in super slow motion. The bullet goes into the block, and then as a result of the collision, the bullet block combo have some velocity which we have to figure out. And so then this velocity is going to carry the bullet block combo of vertical height of 0.1 before it comes to rest for a brief moment. So the way we're going to figure out this velocity immediately after the collision is with conservation of energy. So whenever you do conservation of energy, you need to have a 0 point. So the 0 point for this problem, I'm going to put it as a red line here. This is our 0 point right there. So conservation of energy, kinetic energy initial plus potential energy of gravity initial. There's no spring in this problem, so I'm not even going to mention springs. Plus or minus work non-conservative equals kinetic final plus potential of gravity final. So let's go through the energies. Now the key thing is we're looking at this situation immediately after the collision. So the bullet enters the block, the collision is done, and then the bullet block combo swing upward. So we do start with kinetic because the bullet block combo has a velocity, and that's what we're looking for. Initially, there is no potential of gravity because the bullet block combo start on the 0 point. Work non-conservative, there is none. because we're looking at the problem after the collision has taken place. The bullet enters the block, the bullet block combo swing upward. The only force affecting the motion as the bullet block combo swing up is gravity, and gravity is a conservative force. So therefore, we have no non-conservative forces acting in this situation. Okay, so final. Up here is our final at this maximum height where it stops for a split second. So because it stops for a split second, kinetic final is 0, and we do have potential of gravity because the bullet block combo has risen above the 0 point. So what we're left with is the kinetic energy immediately after the collision is equal to the potential energy of gravity that's gained as the bullet block combo swing up. So now we plug our equations in. Kinetic is 1/2 mv squared, or that's V initial. Potential of gravity is mgh. The m's cancel. And V initial is square root 2gh. And then h is given as 0.1. Okay, so this comes out to be 1.4 meters per second, which is this velocity right after the collision. So now we know, we figured out that this is 1.4 meters per second. So we take that and we plug it in up here, and this gives, so our total mass, block plus bullet, is 2.015 kilograms. We figured out the velocity after the collision by using conservation of energy, and that came out as 1.4 meters per second. And then the mass of the bullet is 0.015. So the initial velocity of the bullet before the collision is 188.06 repeating meter per second. That's the answer to number 1. Now, for the second question, calculating the percent loss of kinetic energy. So let's make some room here. Okay, so percent loss. In general, percent loss is simply the amount lost divided by the initial amount. That's how you calculate percent loss. So I always like to use money as an example. So for example, you start with $100 and you lose 30. That's an easy calculation. If you have $100 and you lose 30, that's a 30% loss. So the way you did that is you said, okay, well, I lost 30. I started with 100. That gives 30%. So in a very similar way, we're going to be doing this with kinetic energy. But before we can do the calculation, we need to know our starting kinetic energy and our ending kinetic energy. What is the starting amount of kinetic energy and what is the ending amount of kinetic energy? So let's figure it out. So kinetic initial, meaning the kinetic energy before the collision, is all in the bullet. The bullet is the only object that has kinetic energy before the collision. The block is sitting here at rest. So kinetic initial is going to be 1/2 mass of the bullet times the velocity of the bullet before the collision, which we now have the velocity of the bullet. So this is 1/2 0.015 kilograms. The velocity of the bullet before the collision was found out to be 188.06 repeating meter per second. Make sure you square the velocity. So kinetic initial is comes out as 265.8 268 joules. All right, so that's our kinetic initial. Put a line right here. All right, kinetic final. So by kinetic final, what we mean is the kinetic energy immediately after the collision. The bullet enters the block, and we want to find the kinetic energy a split second after the collision is done. And we now have the velocity immediately after the collision. We found that out to be 1.4. So the kinetic final is going to be 1/2. So the bullet and the block joined together. They became one object, so we're going to put m1 plus m2 inside parentheses, and then v final squared. So this is 1/2, so the bullet and the block together are 2.015 kilograms, and then the velocity after the collision is 1.4. So this gives us a kinetic final of 1.9747. So this is a dramatic loss of energy. We started with 265 joules and ended with 1.97 after the collision. So if this were money, I'd be upset. $265 down to $1.97. That's a big loss. So our kinetic energy lost, the amount that's lost is the difference between what we start with and what we end with. So we're going to subtract these two. So we lost 263.2933 joules. I'm not rounding yet. So now to find the percent loss, we go to our percent loss equation. Percent loss is just the amount that was lost divided by the initial amount. So in this case here, we lost 263.2933 joules, and the starting amount before the collision was 265.268. And then we multiply by 100 to get it in percent, and this gives us a percent loss of 99.26%. So almost 100% of the initial kinetic energy was lost. And that just goes into, that kinetic energy goes into heat. As the bullet enters the block, it's going to leave a really hot trail, a really hot hole there as it deforms the block.